Streaming? Okay. Hello, everyone. It's 7 o'clock. Let's get started. Clearly, everyone is at the football game right now, so hopefully more people show up. Yeah, you guys are here, so congrats. Good priorities. All right, so my plan is to run through this review that I posted. It's online on UCF Study Union if you want, like, a copy on your computer or something. But I'm going to try to run through everything on this review, and if we don't finish it, I'll post the rest of the answers online on the same site. And if we do finish it, we can just go off whatever you guys want to do. Any questions before I get started? Okay. All right, so question number 1, which of the following is a halogen? What group of the periodic table are halogens? Group 7, right? So if we pull out our periodic table, remember groups are vertical and periods are horizontal. So group 7 is the halogens. So FClBrI. And we've got bromine. That is a halogen. Okay. So what forms an ionic compound? This is between a metal and a non-metal. That's an ionic compound. So remember, again, on the periodic table, your metals are on your left side of the periodic table, and your non-metals are on the right side. So if you have an element on the left side and an element on the right side, that's an ionic compound. Okay. Air is, so this is a review of homogeneous and heterogeneous mixtures. So heterogeneous would be if you can see different parts. So the classic example of this for Gen Chem is a fruit salad. So in a fruit salad, you can see like grapes, watermelons, kiwi, whatever. So if you can visually see each different particle, it's a heterogeneous mixture, but because in air, the particles that are making it up are so small, you can't see them, it's considered a homogeneous mixture. And if I'm going too fast, or if you have any questions, just yell out. I won't get offended or anything. Any questions on those? Yeah. All right. Okay, moving on to number 4. We've got a block of ice, and we're melting it, and we're trying to decide if that's a physical or a chemical change. So when you melt ice, it's still composed of the same materials that ice was. So when you melt ice into water, it's still H2O. So you're not changing the chemical properties of it at all, so it's a physical change. If you're reacting water with something else and changing its composition, that would be a chemical change. Okay. zeros or something. And this is what you get. That would be precise, but it wouldn't be accurate. Let me zoom in a little bit. So if you get this, right, it's precise, but it's not accurate, whereas this would be accurate and precise. So be sure to know the difference between the two of them. Okay. All right, moving on to question 7. This is everyone's favorite topic in Gen Chem, is significant figures. So we have 0.001. So how many sig figs is 0.001? 1 sig fig, right? So these zeros don't count, so we're left with just 1 significant figure. Any questions on that? Okay. 7b, 850,000. Remember that trailing zeros never count for significant figures, so we're left with just 2 sig figs. Okay. C, 208. Remember that zeros in between 2 significant figures, so 2 non-zero numbers, always count. So here we're left with 3 significant figures. And then 16.00. I believe this would be 4 significant figures because of the decimal point trailing. So 4 sig figs. Okay. So for problem number 8, we have 132.08 plus 35.978. So with adding and subtracting, we have a rule for significant figures. And who knows the rule? What's the rule for adding and subtracting? Yeah. Great. The least number of numbers after the decimal point, right? So least number after the decimal point. So for 132.08, we've got 2 numbers after the decimal point. And for this number, we have 3 after the decimal point. So when we add them up, 132.08 plus 35.978. So if you put that in your calculator, you're going to get 168.058. But we know for these numbers, for adding and subtracting, you know, you're going to round so that you have two numbers after the decimal point. So you're going to end up with 168.06 as your final answer. Okay. So now we have number 9, solve 25.8 times 12. So for adding, or for multiplying and dividing, our rule is the least number of significant figures overall. So the least number of SF. So when we do this, 25.8 has 3 significant figures, 12 has 2 significant figures, so 25.8 multiplied by 12 is going to give you 309.6, but we're going to round that to 310, right? Because that 0 and 310 is not significant. Okay, any questions on that? Be sure to know your rules for multiplying and dividing versus adding and subtracting, because they are different. All right. So for number 10, I'm going to go over really quick the form that all of the elements are in. So we have this AZX, right? So X is the element, Z is your number of protons, and A is protons plus neutrons. So your bottom number is the number of protons, which is also the atomic number of your element. So your top left number is protons plus neutrons, and then you're going to have some element there. All right. So our first one, we have 70, 35 bromine. So the number of protons would be 35, right? Just the bottom number. The number of neutrons is the number of protons plus, so it's 35 plus 35 equals 70, right? So this top number is neutrons plus protons. This is just protons. So if you subtract 35 from 70, that's going to give you the number of neutrons, which is 35. And the number of electrons. So this bromine has no charge, which means that its number of protons and its number of electrons is perfectly balanced. So it's also got 35 electrons. So 35 for all three particles there. Okay. So moving on to part B, we've got nickel 2+. So the number of protons, again, is just the bottom number. So that's 28. The number of neutrons is this top number minus the bottom number, which is 22. And for electrons, we see that nickel has a positive charge, which means it must have more protons than electrons, and specifically 2 more protons than electrons. So if our number of protons is 28, our number of electrons is 26. Any questions on that? Remember that positive charge means you have more protons. Okay. So for part C, we've got magnesium 2+, and we've got the top number, but we don't have the bottom number. So to figure that out, remember that the bottom number is your atomic number. So if we pull out our periodic table, remember the atomic number is the number in the top left. So for magnesium, it's 12. So zooming out, we put a 12 here. So our number of protons is 12. Our number of neutrons is 35 minus 12, which is 23. And our number of electrons, we have another +2 charge, which means we have 2 more protons and electrons. We have 10 electrons. Okay. Part D, we've got oxygen 2-. So again, protons is 16. Neutrons is 24 minus 16, so that's 8. And then our number of electrons, here we have a negative charge instead of a positive charge, which means we have more electrons than protons. And the charge is 2-, so we must have 2 more electrons. So 18 electrons. Any questions on that? Okay. I'll give you guys a second to write it down. All right, so number 11, we're dealing with isotopes. So we have which of the pairs are isotopes? Let me zoom in a little bit more. Okay, so we've got a pair with a different number of protons and a pair with a different number of neutrons. So remember that isotopes mean different number of neutrons. So 25 and 26 mean that these two elements are actually different, so they can't be isotopes. So that means that answer B is correct because they both have the same number of protons. Remember, that's the atomic number. So they're the same element, but they've got different numbers of neutrons because they have different top numbers. So B is indeed your answer. Okay, any questions on isotopes? This means different number of neutrons. All right. Okay, so now we're moving on to a little dimensional analysis dealing with Avogadro's number, which you all should hopefully know by heart for the test. And here we're going to deal with converting grams to moles. So a one-step process, but just to refresh your memory. Remember, for converting from grams to moles, we have this concept of the molar mass. So in 1 mole of lithium, we've got, and you determine this from the periodic table. So this bottom number here, the 6.941, that's your molar mass. So that shows you how many grams are in 1 mole. So for lithium, it's 6.94. That's how you find the molar mass, in case you forgot. So 6.94 grams. Okay? And then same thing with neon. 1 mole in the molar mass of neon is 20.18 grams. So you get 0.40 moles of lithium. And you get 1.98 moles of neon. It's important to remember how to do this because you're going to be using molar mass and conversions a lot when we get to stoichiometry. So having this down is really important. But remember, you find these numbers from the periodic table, and they're all going to be given to you for the exam. Okay. So for 13, how many atoms are in the following? So we're going to do a similar process to number 12. We're just adding one more step. So 6.022 times 10 to the 23rd is the amount of atoms in 1 mole. So we can use Avogadro's number to figure this out. So in 1 mole of bromine, we have 79.90 grams. And then in 1 mole of bromine, I've got 6.02 times 10 to the 23rd atoms. So that's actually what Avogadro's number is saying. It's saying that there's 6.02 times 10 to the 23rd particles in 1 mole of an element. So that's 9 times 10 to the 22nd atoms. Okay. Does anyone need me to go over how to do scientific notation on the calculator? Does everyone know how to do that? Okay, I'm not seeing any hands. So yeah, make sure you know how to do that for the exam. All right, so for calcium, same process. 1 mole of calcium is equal to 40.08 grams. And then in 1 mole calcium, there's 6.02 times 10 to the 23rd atoms. So that leaves you with 4.5 times 10 to the 23rd. All right. Moving on, what group number is the pnictogens? So we can go over a little bit of group names. So I always remember that the pnictogens are the group with P and N in them. So this is group 5. Pnictogens is group 5. Remember the halogens are group 7. Then we've got our noble gases. Okay, and then for the metals, this is alkali. Group 1 is alkali metals. And group 2 is alkaline earth. And everything in here, in the middle of the periodic table, remember, are the transition metals. Okay. So make sure you know your group names and then the charges associated with all these different groups. Okay. So group 5. All right, so for 15, which pair of elements are the most similar? So if you get this question on the exam, you're going to search for elements that are in the same group. Remember, the group is the vertical part of the periodic table. So elements in the same group, what do they share? That would make them similar. Yeah. Great, yeah. The amount of valence electrons, right? That's what each group is organized by. So group 7, the halogens, they all have 7 valence electrons. 7 electrons in their outermost shell. So if you have the same number of electrons in your shell as another element, that means that you and that element are going to react the same way or similarly. So if you get a question asking about which elements are the most similar, go with the ones in the same group because they're going to react similarly. So for 15, Br and F are both halogens, so that's going to be the pair that reacts the same. Okay. Any questions on that? Valence electrons? Okay. So here we have what is a cation, and that is just a positive ion. Remember that an anion is a negative ion. And how I remember this is that people usually like cats, so cats are more positive, and anion kind of sounds like onion. I'm not a big fan of onions. So, I mean, use whatever works for you. That's always worked for me. Also, the T in cation looks like a plus sign. So, a lot of ways to do it. Okay. So, question 17. What is the charge of the halogens? So, again, periodic table. Group 7 is the halogens. How many electrons make a full shell? It's 8, right. 8 electrons. So, as you go to the right in the periodic table, these elements are getting more and more electrons in their valence shell. So group 7, the group numbers actually tell you how many valence electrons the element has. So the halogens are in group 7, which means they have 7 valence electrons. So 7 valence electrons would mean that it is way easier for them to get to the stable configuration of 8 electrons if they gain an electron, right? So gaining an electron means you're gaining a negative charge, and they need 1 more electron in their valence shell, so the charge is going to be -1. -1. To use that same methodology, let's go over the alkali metals. So all these alkali metals have 1 electron in their valence shell, so it's way easier for them to lose the electron than to gain 7 electrons for stability. And if you lose an electron, you're losing negative charge, which means you're getting more positive. And for them, they just lose the 1 electron, so they have a charge of +1. Don't try to apply this to the transition metals, because remember, they can have variable charge. Okay. All right. So now we're dealing with naming. I'm going to do this on a separate sheet of paper. Okay. So for A, we have MgCl2. So I'm going to do a little bit of a clinic on naming here in the next 3 sets of problems. So magnesium chloride, right? If we look at the periodic table, magnesium is over here with the metals. It's right there. Chlorine's over here with the nonmetals. And when a metal and a nonmetal pair up with each other, we call that an ionic compound. So for ionic compounds, your cation, right? You just use the name of your cation, which is your positive ion. So periodic table name. So for this problem, magnesium is our positive ion. So the first part of the name is just magnesium. The anion, which remember is the negative ion, you're going to use the periodic table name, but you're going to add this "ide" suffix, right? So chlorine becomes chloride. So magnesium chloride. Any questions on that? Okay, that is your formula for all ionic compound names. They're the easiest to name. Okay. So for B, we've got CdBr. And if I check my periodic table, I see that cadmium is right here. And it is in the middle of the periodic table, which means it is a transition metal. So transition metals have variable charge. So trans metal is variable charge. And because they can have a variable charge, when you're naming them, you need to account for the charge in the name. So for magnesium chloride, magnesium is an alkaline earth metal, so we know it has a stable charge of +2. So we don't have to designate that in the name. But for cadmium bromide, cadmium is a transition metal, so we don't know its charge necessarily. It can have variable charge. So you figure that out from the anion. So bromine is the halogens right here. And we know the halogens have a -1 charge. And this compound is neutral. There's no net charge. So I know that the charge on cadmium has to be +1. So, and you have to use Roman numerals for this, I would call this cadmium 1 bromide. Cadmium 1 bromide. Because the transition metals have variable charge. Yeah. Right, yeah. So even if it is only 1, you still have to designate that, because this cadmium could pair up with like oxygen or selenium or something. So even if it's just +1, you still have to show it in the name. Good question. All right. So problem C. You've got P4F8. So periodic table again. Phosphorus and fluorine are both on the right side of the periodic table, which means they're both nonmetals. And when two nonmetals bind together, that's called a molecular compound. And for molecular compounds, you're using those numerical prefixes. So P4F8 is tetraphosphorus. Remember, tetra is for octofluoride. Remember, you're still following that same rule of the first element, you're listing out its full periodic table name, and the second element, you're adding that IDE suffix. So tetraphosphorus octofluoride. All right. D is NaBr. Again, sodium's on the left side of the periodic table, bromine's on the right, so this is ionic. So we just use the full name of Na and then add that IDE suffix. Sodium bromide. Okay. So any questions on this part of naming? Yeah. That's a good question. So let me use an example for that. So the answer to that is no, you wouldn't. If you have one of each element, so let's say you have CO, you only use mono for the second element, right? Because this is carbon monoxide. So you're only using that mono prefix for the second element, not for both. Okay, good question. All right, moving on. 19 is more naming. The first one is NO3 minus. What is that called? Nitrate. Good. Nitrate. Please practice your polyatomic anions, because they will be on there. Okay, B, we've got Cu NO3. All right, so let's check the periodic table. Copper is right here, which means it's a transition metal, which means it has variable charge. So we're going to have to use those Roman numerals. Nitrate, we just saw, has a charge of -1. This compound is electrically neutral, so that means that copper has to have a charge of +1. So copper, 1. And when you have polyatomic anions, you keep the name. So this isn't nitride, it's nitrate. So when you're dealing with like phosphate or sulfate or something like that, you're not changing that name. So that becomes copper 1 nitrate. Okay. C Li2SO4. All right, so if you look at your periodic table, lithium's right here, which means it's not a transition metal. So this is just an ionic compound. So lithium sulfate. Because SO4 is sulfate. Remember, SO4 has a charge of 2-. Okay. All right, so now we have 21. How many moles of phosphate ions are in 20 grams of calcium phosphate? So let me do this on paper. So we're looking for moles of phosphate in 20 grams of Ca3. Oh, I skipped a question? Dang, okay. Yeah, we almost didn't name these acids. All right, good call. I know, it's a big miss. Okay, H3PO4. Let's go over acid naming. All right. Anything that ends in 8, any polyatomic anion that ends in 8 is going to become ic acid. Anything that ends in ite, sulfite, phosphite, whatever, is OS acid. So we've got 8 is ic acid, ite, OS acid. And if we've got something that ends in ene or ide, so if you've got chlorine, fluorine, whatever, it becomes hydro, whatever the acid is, or whatever the anion is, ic acid. So, H3PO4. What is PO4? Phosphate. Good. So it ends in 8. Which means this is phosphoric acid. You've got that ic acid. Okay. HBr. Here we've just got a regular old bromine. It's not a polyatomic anion, so we can just do hydrobromic acid. Remember, you've got that hydro blank ic acid formula. Yeah. No, because HBr is an acid. Yeah, good question though. So hydrogen bromide would not be a correct name. You have to say that it's an acid. And then finally, H2SO3. What is SO3? It's sulfite. So that means you've got the OS acid suffix, so it becomes sulfurous acid. Okay. So back to 21. Remember, we've got 20 grams of calcium phosphate, and we're trying to figure out how many moles of phosphate ions are in 20 grams of calcium phosphate. Okay. So the first thing I'm going to do is, since I'm looking for moles of an ion, I'm going to convert this compound to moles. So in 1 mole of calcium phosphate, I'm going to figure it out based on the periodic table, because that's what you're going to have to do on the test. So calcium has a molar mass of 40.08, and I've got 3 of those. plus 2 phosphorus. Remember that this 2 means you're multiplying everything in the parentheses by the subscript. So I've got 2 phosphorus, and I've got 8 oxygen. So phosphorus is 30.97. And then I've got 8 oxygen, and each oxygen is 16 grams. Okay. So I got 310.18. And for stoichiometry, you don't really have to worry about the sig fig rule, so you can just leave it at this because your answers are going to be close enough. So 310.18 grams. And how many moles of phosphate ions do I have in 1 mole of Ca3PO4 2? So remember, phosphate is PO4, and this formula is telling me I've got 2 of them. So in every 1 mole of calcium phosphate, I've got 2 moles of phosphate. And that's going to give me my answer. So actually, the hardest part of that problem was figuring out the molar mass. So 0.13 moles of phosphate ions. Any questions? Yeah. Yeah, so you can round oxygen to 16. You can make nitrogen 14, carbon 12. Hydrogen, you can just make 1, stuff like that. If they're close enough to the whole number, you can just round it. Yeah, you'll still get around the same answer if they're close enough. Good question. All right, so that's moles of ions. Okay, for 22, we have, write the empirical formula of the following formulas. So remember, empirical formula is your lowest whole number ratio. So when I'm looking at these problems, I'm checking to see if they have the lowest whole number ratio of all the elements. So problem A, I've got C2H4. So I can divide both of these by 2. So the empirical formula is CH2. For B, I've got C3H7. And there's no common factor there between the 3 and the 7, so the empirical formula is just as is. For part C, I've got C8H24O16, so I can divide all of these by 8, and that's going to give me CH3O2. Okay, any questions on empirical formula? All right. So we're going to get to some math stuff now. So we've got 23, determine the empirical formula of a sample containing 3.04 grams of nitrogen and 6.94 grams of oxygen if its molar mass is 92.04 grams per mole. So I've got nitrogen, I've got 6.942 grams of oxygen. My molar mass is 92.04 grams. So the structure for solving these problems is to convert your grams of each element to moles, and then you divide everything by the lowest number of moles. So I can take 3.04 grams of nitrogen, and in 1 mole of nitrogen, I've got 14 grams of nitrogen. Then I can take oxygen, 6.942 grams of oxygen, and in 1 mole, I've got 16 grams. So that gives me 0.224 moles of nitrogen, and 0.44 moles of oxygen. So on the final, if you get an empirical formula problem, it's going to have numbers that work out nicely like this one. If you get some weird number that can't be divided correctly, you know you did something wrong. So I can divide both of these by the lowest number. That gives me 1 nitrogen and 2 oxygen. So 2 oxygen. So the empirical formula is NO2. Any questions on that? Yeah. Yeah, the molar mass is just like information that could kind of like throw you off. You'll see that sometimes in tests they'll do that. They'll give you like info that's not needed, so just be wary of that. So again, all you're doing is you're taking your given grams of the elements and then figuring out how many moles of each element you have and then dividing by the lowest number of moles. That's your process. Okay. So 24, determine the empirical formula and molecular formula of a combustion reaction. So remember that a combustion reaction, you're taking an organic compound, reacting it with oxygen, and it's going to make CO2 and H2O. So let me make it bigger. So I've got 57.28 grams of CxHyOZ, 176.04 grams of CO2, and 54.06 grams of H2O. Sorry, my handwriting is so bad. Okay, so with these problems, you're going to work with carbon dioxide to get your carbon, and you're going to work with H2O to get your hydrogen. So our first step in this problem is we're going to convert both of these into grams of the substance we're looking for. So CO2 we're going to convert to grams of carbon, and then H2O we're going to convert to grams of hydrogen. Once we have our mass of carbon and our mass of hydrogen, we can figure out how much oxygen we have because they give us the total mass of the organic compound. Okay. So 176.04 grams of carbon dioxide. I'm converting to grams of carbon. So 1 mole of CO2 is 44.01 grams. And in 1 mole of CO2, I've got 1 mole of carbon. And then finally, in 1 mole of carbon, I've got 12 grams. So that gives you 48 grams of carbon. Now we'll do hydrogen. So I've got 54.06 grams of H2O, 1 mole of water is 18.02 grams. I've got 2 moles of H for every 1 mole of H2O. And 1 mole of H is about 1 gram. Let's call it 1.01. So that's about 6 grams of hydrogen. Okay, so now that we have our grams of carbon and our grams of hydrogen, we can figure out our grams of oxygen. So for grams of oxygen, we can take 48 or 57.28 minus 48 plus 6. So 57.28 minus 48 plus 6. If you do that, you get 3.28 grams of oxygen. All right, so now I can take, now that I have my mass of all my elements, I can convert them all to moles and then go from there. So I've got 48 grams of carbon, 48 grams of carbon. And I know that 1 mole of carbon is 12 grams. So that's going to give me about 4 moles of C. And 6 grams of hydrogen times 1 mole of hydrogen is about 1 gram. That's going to give me 6 moles of H. And then I've got 3.28 grams of oxygen. And that's about 16 grams. That's going to give you about 0.2 moles of oxygen. So our next step, remember, is to divide everything by the lowest number. So that's going to give me 1 oxygen. That's going to give me 30 hydrogen. And it's going to give me 20 carbon. Okay. So that's going to give me a total compound, a total molecular formula, if I write it out, of C20H30O. Okay. Is this the molecular formula? Yes. Is it the empirical formula? Yes, because it's our lowest whole number ratio, right? So you can have compounds that are both the molecular and the empirical formula. So I've only got one oxygen, and I can't make that a smaller whole number. So that's both the molecular and the empirical. So it's MF and the EF. Okay. Any questions on this whole mess? There's like a lot of steps. Yeah. Yeah, so good question. So if you do get a situation, right, where you're dividing by 1, that's going to give you the empirical formula always because you're going to get 1. But there are some instances where they'll give you like a molecular formula, and you'll have to find the empirical formula. But yeah, since you're dividing by the smallest, you're always going to get 1, which means you've got the empirical formula. Good question. All right. Okay, so now we're going to do a little bit of reaction stoichiometry. So problem 25, calculate the mass of propane needed to react with 35 grams of oxygen. So the mass of propane needed to react with 35 grams of oxygen, O2. So with these problems, always start out with the value that you're given. You're going to do stoichiometry for anything that looks remotely like this. And you're always going to use your starting value as the value given to you in the problem. And for these reactions, the coefficients matter. So always make sure you have a balanced equation. You should be given an already balanced equation, but it's not going to hurt to double check just in case, because the molar ratio matters. So we've got C3H8 plus 5O2 yields 3CO2 plus 4H2O. All right. So starting with what we're given, 35 grams of oxygen. And this is a little tricky. In 1 mole of oxygen, of O2, how many grams do I have? Good, 32. Thanks, Ethan. So since this is O2 and not just oxygen, I have to account for it being diatomic. So I'm going to get 16 multiplied by 2, which is 32. Any questions on that? Because that's like a very easy way to trip up. Yeah. So if it's diatomic in the reaction, oxygen isn't always diatomic. But if it's diatomic with the subscript 2, then you have to use that mass. Yeah, so it's different than the other problems. So like for this problem, when we were looking at finding the empirical formula, we were just given grams of oxygen by itself, so we used 16 grams. But they'll always designate if you have O2 or just O. Good question. So 32 grams of oxygen is 1 gram of O2. And the next part, to convert to moles of propane, you have to look at your balanced equation. So for every 5 moles of O2, I know that I have 1 mole of propane. But always check back to your balanced equation. And now I just have my final step to convert this to grams. And 1 mole of C3H8. Remember, each carbon is about 12, each hydrogen is about 1. So I've got 36 plus 8. That's 44 grams. So 9.63 grams of propane. Anyone need clarification with this problem? Use the balanced equation to your advantage. Rude. Okay. All right, so now we have a limiting reactant problem. So I'm going to rewrite it. All right, so I've got sodium chloride reacting with HBr to make NaBr and HCl. And I'm given that I've got 30 grams of HBr and 20 grams of NaCl. So remember, your limiting reactant is the reactant that limits the product. So what we're going to do for limiting reactant problems is figure out how many moles of a certain product that each one of these reactants make. And when you're doing these problems, you have to pick the same product to figure out the amount of for both reactants. So if I pick on sodium bromide, I have to find how much sodium bromide is made by NaCl and HBr. I can't use different products, if that makes sense. All right. So remember, start with what you're given. I've got 20 grams of NaCl. I'm going to convert that to moles. So 1 mole of sodium chloride is equal to, where's my periodic table? 22.99 plus 35.45, which is 58.44 grams. And let's pick on sodium bromide as our product. So for each mole of NaCl, I make 1 mole of NaBr. So it's a 1-to-1 ratio. So that gives me 0.34 moles of NaBr. .30 grams of HBr and 1 mole, I've got about 90 grams. Right? Let's do 79.904 plus 1.008. So, oh, 80, just kidding, not 90. 80.912. And again, that's a 1-to-1 ratio. And that gives me 0.37 moles of NaBr. So our limiting reactant is sodium chloride. Remember to use the same product for these problems. So pick on the same compound. Okay. I'm pretty confident you're going to have to do something like that. So know how to do it. All right, 27. What is the formula for percent yield? Percent yield is equal to actual over theoretical times 100. All right, let's mess around with this a little bit more. So we know it's actual over theoretical. So actual, that's found in the lab. So if you do an experiment with other chemists, your actual yield is going to be the one you find in the lab. Your theoretical yield, however, is the max ideal yield. So the theoretical yield is found out through stoichiometry, and that's the most amount of product you can ever make. It's never reached because there's always some sort of human error or complications. So your percent yield should never be over 100%. It shouldn't even really be that close. An average yield when you get to like Orgo lab, an average yield for Orgo labs is about 30%. So you're never going to get anywhere close to theoretical in the lab. Okay. So for the percent yield problems, they'll always give you the actual yield, and you have to figure out the theoretical yield and then figure out what percent that is. So for problem 28, we've got silver chloride reacting with copper 1 bromide to produce silver bromide and copper 1 chloride. And we're trying to find the percent yield when 30 grams of silver chloride reacts with 10 grams of copper 1 bromide and produces 8 grams of CuCl. So 8 grams, that's our actual yield. And what we're going to do here is stoichiometry to figure out our theoretical yield. All right. So you have to figure out which one of these two reactants is your limiting reactant in order to figure out the theoretical yield. So let's do that first. So I've got 30 grams of silver chloride and 1 mole. I've got 107.87. That's 35.5. 143.32 grams. 1 mole of AgCl, and then it's a 1-to-1 ratio. Let's pick on AgBr. So that gives me 0.21 moles. AgBr. So that also gives me how many moles of copper chloride, which we should actually be, that's the one we should be picking on because we're given the actual yield of that. So CuCl, it's a 1-to-1 ratio across the board, so you're making 0.21 moles of both these products. So 0.21 moles of CuCl. Now we've got 10 grams of copper 1 bromide. And the mass of copper bromide is 143.45 grams times 1 mole of CuCl over 1 mole CuBr. So that gives me 0.07 moles. Okay. So as we can see, the copper bromide is the copper 1 bromide is the limiting reactant, and it produces 0.07 moles of CuCl. And what we're going to do is we're going to figure out how many grams of copper chloride that makes, then compare it to the actual yield. So 0.07 moles of CuCl. And I know 1 mole of CuCl is 99 grams. So what I'm actually going to find, and this is an error on me, so you get 6.93 grams of the CuCl. So let's change, just to make sure I'm right, let's change the actual yield to 5 grams. So now I've got 5 grams of CuCl. So this is our theoretical yield. And to find the percent yield, we're going to take the actual over the theoretical times 100. So 5 over 6.93 times 100, which is 72.15%. That's our percent yield. Yeah. I switched it from 8 to 5 because 8 would mean that we have more actual than theoretical. 8 would mean you have more actual than theoretical, which doesn't happen. So when I did this problem, I just made a calculator error, I guess, when I was making it. So the actual yield has been changed to 5. That's not what it is on the review. It's 8, but we're changing it to 5. It's the same process. I mean, you could put 8 here and you'd still figure out a percent yield. It would just be over 100. Okay, so remember for percent yield problems, if they don't already tell you the limiting reactant, you have to find it first and then figure out how many grams of product that makes. Then you take that gram of product and you compare it to the actual yield, which will be given, and you'll find the percent. So you're always going to be given a reaction. You're always going to be given either mass of the 2 reactants or which one is in excess. So this problem may say that assume that copper bromide is in excess or something like that, and that clues you in that AgCl would be the limiting reactant. Okay, any questions on percent yield? All right, moving right along. Question 29, what is the universal solvent? Water. One more time. Water. So, also known as H2O. So, if you have any problems asking for the solvent and water is involved, even if it's like 1% water, your solvent for that mixture is always water. Always, 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 always water. All right. So let's go over what a solvent is. So solvent is highest percentage in mixture. your solvent is your highest percentage in mixture. That always will apply unless you're dealing with water, which would then be the solvent. Okay? So here we're given a mixture of 30% methane and 70% propane. So our solvent would be what? Propane. Good. If it was 29% methane, 70% propane, and 1% water, the solvent would be water. All right, 31, equation for molarity. What's our equation for molarity? You should all know this. M, molarity is moles over liters. All right, so let's do some problems with molarity. So, 32, I'm just going to rewrite. All right, so what is the molarity of a 20 gram, 0.8 liter copper 2 chloride solution? So I know that molarity is moles over liters, and I'm given grams, and I'm given liters. So liters, I'm good. Grams, I need to convert to moles. So 20 grams of CuCl2 molar mass of copper 2 chloride is 134.45 grams, which gives 0.15 moles of CuCl2. So now to figure out the molarity, I can just take 0.15 over 0.8, which was my given volume, and I get 0.185, 0.186 molarity. Always be converting to moles over liters for these problems. Oh, 0.8. I'm sorry. That's a terrible 8. Okay. So problem 33. Calculate the volume of solution made by diluting 50 milliliters of 0.2 molar sodium hydroxide to 0.05 molar. What's our formula for dilution? I'll just give it to you. M1V1 is M2V2. That should be ringing a bell, hopefully. So you just take, this is M1, this is V1, this is M2. So remember we have to convert to liters, so that's 0.05 liters times 0.2 molar equals 0.05 molar times volume 2. So you get that your volume is 200 liters. Or 0.2 liters. 0.200 liters. So anytime you see dilution, you should be thinking M1V1 is M2V2. And you'll be given 3 of the 4 variables, and you'll just have to find the 4th. All right. So for this next problem, we're looking for what volume of 0.2 molar lithium nitrate is required to react with 100 milliliters of 0.1 molar sodium chloride. So if I write out my equation, yeah, I'm going to label everything, so it'll be okay. Plus NaCl yields NaNO3 plus LiCl. So I've got 0.2 molar, and I've got 100 milliliters and 0.1 molar NaCl. Yeah. I'll just do that right now. We good? Okay. All right, so I'm looking for volume of lithium nitrate. So I've got, I don't know, liters. So since this equation is 1-to-1 across the board, we can use M1V1 equals M2V2, but I'm going to do it the hard way with stoichiometry, because it's very likely that if you get this problem on the final, it's not going to be 1-to-1. So molarity is moles over liters. So if I know 2 of the variables in equation, I can figure out the 3rd. So M is moles over liters. M is moles over liters. I've got 0.1 molar and 0.1 liters. So 0.1 molar is moles over 0.1 liters. So that means I've got 0.1 for moles. So 0.1 times 0.1 is 0.01. That's how many moles I have. Moles of NaCl. So because it's 1-to-1, I can also say that I have 0.01 moles of lithium nitrate. So 0.01 moles of NaCl times 1 mole of NaCl for every 1 mole LiNO3. That means I've got 0.01 moles of lithium nitrate. And now that I've got 2 of the 3 variables, I can figure out my volume. So again, M is moles over liters. I've got my M and I've got my moles. I'm looking for liters. 0.2 molar is equal to 0.01 moles over liters. So 0.200 times L is equal to 0.01 moles. Divide both sides by 0.2. And you're going to get that L is 0.05 liters. if you do get 1-to-1, you can just do this, right? So lithium nitrate, I'll make my 1. So I've got 0.2 times V1 equals 0.1 times 0.1. And then you'll get the same thing. So those are two ways to do it. One of them is way easier. So if you get 1-to-1 on the exam, just do that formula. It'll save you a lot of time that you'll need. Any questions on this? Explain all of it? This part? Okay, yeah. So molarity is moles over liters, right? So through stoichiometry, through the molarity equation first, actually, I figured out my moles of sodium chloride, right? Both of these values were given to me in the problem, the volume and the molarity. So using the molarity equation, I figured out my moles of NaCl. Then I did stoichiometry, right? Because it's a 1-to-1 ratio in the reaction. So for every 1 mole of sodium chloride, I've got 1 mole of lithium nitrate. That gives me 0.01 moles of lithium nitrate. I'm looking for the volume of lithium nitrate. I know the molarity, and now I know the moles. Molarity is moles over liters. I know 2 of these variables. I can solve for the third. So 0.2 molar, which is given, equals 0.01 moles, which I found, over liters, and then you just solve for liters. Does that make sense? Okay. Any other questions, comments, concerns? Okay. That's about as tricky as the molarity problems should get. So if you feel good on that, you should be okay. 35 is just a definition, defines salt. So salt is an ionic compound without O2 minus or OH. All right. Difference between an electrolyte and a non-electrolyte. What does an electrolyte do in solution? It completely dissolves, right? A non-electrolyte does not do that. So that's your difference. All right, question 37. What does aqueous mean? Soluble. So on the final, if you look at the reactions that are relating to solubility, it's very likely he's going to tell you which ones are soluble and which ones are insoluble. So for this reaction, we're trying to figure out the net ionic equation. Make it easier for yourself. It'll probably tell you which one is insoluble, right? This solid means that that lead chloride, the lead 2 chloride, is insoluble. Aqueous means it's soluble. I really want to hammer that home because it makes it way easier when you're doing these problems. All right, let's do 39. So we're going to figure out the net ionic equation for 2AlCl plus PbBr2 yields PbCl2 plus 2 LBr. What does aqueous mean? Soluble. Which one of these compounds is insoluble? Good, lead 2 chloride. All right, so let's write the net ionic equation. So remember, if something is aqueous, if something's soluble, they're going to dissolve completely in a reaction. So are these two compounds strong electrolytes? Or just electrolytes in general? Yes, is the answer. They're both electrolytes. So when you write out the net ionic equation, the coefficients matter and the amount of bromines matter. Or the amount of the subscripts matter. That's what I'm trying to say. So make sure you account for those. So I'm going to write everything is going to completely dissolve. Aluminum is a transition metal. It's paired up with 1 chlorine, so I know that aluminum is +1. So I've got 2 Al plus 2 Cl minus. Next compound. Bromine has a -1 charge. I've got 2 bromines, I've got 1 lead, and the compound's neutral. That means that lead has a +2 charge. So plus Pb2 plus 2 Br minus. Yields. PbCl2 is insoluble, so it's not going to dissolve into its ions. It's just PbCl2. Aluminum bromide, 2 Al plus 2 Br minus. So that is the equation the ions we're working with here. All right, so now I'm going to cross out stuff. What is the stuff I'm crossing out called? Spectator ions. Good. So aluminum and aluminum ion and bromine ion are my spectator ions. So they cancel out. And I'm left with the net ionic equation. 2Cl minus plus Pb2 plus yields PbCl2. Net ionic equation. It's way easier if you don't have to try to read the solubility rules and then solve the problem. Look for that S. Any questions on that? Spectator ions. Okay. Moving on. Now we're going to identify some acids or bases. What is that? Acid or base? Base. Anything with an OH. Anything with OH is a base. HCl, what is that? Acid. This is a strong base because it's a group 1 or 2 metal. This is a strong acid. C. HClO4. This is a strong acid. What about hydrofluoric acid? Is that strong or weak? Okay, it's a weak acid, and it's the only halogen that makes a weak acid, so watch out for it. There's a good chance you'll see that. So they might try to trick you. HF is a weak acid. Okay. So group 1 or 2 metals plus a hydroxide means a strong base. For the strong acids, you just kind of have to memorize. My advice would be just memorize the strong acids and strong bases. Then if you see something that's not what you memorized, it means it's weak. All right. So 41, what is the neutralization reaction? Acid plus base yields a salt plus water. So an acid and a base are going to react to form a salt and a water. All right, 42, what is the redox mnemonic? So for redox, we have a mnemonic we work with. There's multiple actually, but the main one is oil rig. Remember, oxidation is loss, reduction is gain. And this is referring to loss and gain of electrons. So that's the mnemonic, oil rig. All right, so 43, we're going to be assigning oxidation numbers. And we've got 4 options here. So Br2, remember that the halogens are diatomic in their elemental form. So anything in its elemental form has an oxidation number of what? 0. Good. So bromine, 0. For Mg2+, any ions, the oxidation number is the charge on the ion. So the oxidation number is +2. Here we've got iron in its elemental state, so it's 0. And here we've got oxygen in its elemental state, also 0. Any questions on that? If something is in its elemental form, like a metal by itself, it's going to be 0. So oxidation is loss of electrons. So if something gets oxidized, its oxidation number is actually going to go up. Good question. All right, so now let's figure out the oxidizing agent for this problem. So this is question 44. All right, we have AgCl3 plus Fe yields FeCl plus Ag. Okay. So oxidation numbers, you can go through the same methodology you would to figure out the charge on something. So chlorine is a halogen. Its charge is always -1. So its oxidation number is always -1. And there's 3 of them. So -1 times 3 is -3. Silver, remember this is a neutral compound. There's no net charge. So silver has to have a charge and an oxidation number +3. What's the oxidation number of iron? 0. Good. All right, moving on to FeCl. Chlorine, again, halogen, standard charge, standard oxidation number, -1. Neutral compound, just 1 iron, +1 oxidation number. Silver by itself, 0. Okay. So this question is asking for the oxidizing agent. So the oxidizing agent, remember that this is backwards. It's actually the substance that gets reduced. So it's tricky, it's flipped. But be sure to remember that it's flipped. The reducing agent is the substance that gets oxidized. All right. So you are oxidized if your oxidation number increases. Reduced if your oxidation number decreases. All right. Which one of these elements gets reduced? Silver, good. So silver is reduced. Right? Silver went from an oxidation number of +3 on the reactants to 0 in the products. Chlorine keeps the standard oxidation number in both, so it's neither reduced nor oxidized. In iron, goes from an oxidation number of 0 to +1, so iron gets oxidized. Knowing that, which one of these two is our oxidizing agent? The silver. So silver is the oxidizing agent. Iron is the reducing agent. Any questions on redox? Clarifications? All right. Moving on to the last page. Find the heat energy when 20 grams of water is heated from 200 Kelvin to 310 Kelvin. What formula do we have to use to solve this problem? MCAT, good. Q equals MC delta T, where M is mass, C is specific heat. So on the final, you will always be given the specific heat of a substance unless it is water. You're expected to know what water is. What is the specific heat of water? Good. So the specific heat of water is 4.18. You have to know that number. It's not going to be given to you. So if it's anything else, if it's iron or copper or chromium or something like that, they will explicitly give you the specific heat, but you're expected to know water. So no 4.18. And from there, it's just plug and chug. So we have 20 grams as our mass. Our temperature final is 310. Our temperature initial is 200. So our delta T is 110. And we know our specific heat of water. So Q is 20 times 4.18 times 110. That'll give you the answer. All right, 46. Try and fold this. Okay, so a block of ice has 24 joules of work done to it and absorbs 60 joules of heat, and we're looking for delta E. So what's our equation for delta E? Q plus W, where Q is heat energy in joules, and W is work, also in joules. If you see a problem like this, you should draw yourself a little system and surroundings diagram. So our system for this problem is the block of ice. And everything else outside of that block of ice is known as the surroundings. So it could be a tree, the sun, the entire universe. It doesn't matter. We're just looking at the system. All right. So we're told that our system has 24 joules of work done to it. So I've got a work of 24 joules going into the system. And it also absorbs 50 joules of heat, right, from the surroundings. Okay. So remember the first law of thermodynamics? Energy is neither created nor destroyed, right? So everything that happens to the system, the reverse of that happens to the surroundings. But for these problems, we're always just looking at the system. So the system gained 50 joules of heat and had 24 joules of work done to it. So that means that both of these numbers are positive. Remember that this is your Q, and that's your W. So the delta E is positive 50 plus positive 24, positive 74 joules. All right. If it says something like releases 24 joules of heat or does 30 joules of work to the surroundings, those values are negative. If it's to the system, it's positive. Any questions on delta E? All right. 47. How many joules is a nutritional calorie? So nutritional calories are big C calories. There's also small c calories, right? Big C calories, 4,184 joules. Small c calories, 4.184 joules. Notice that's also the specific heat of water. So nutritional calorie is big C, 4,184 joules. Don't put 4.184 joules. All right, now we're moving on to our last problem of the review. It's been a roller coaster. Okay, so here we're given information about a gas, and we're trying to find the delta E. So remember that delta E is Q plus W. So we're given Q explicitly, gives off 100 joules of heat. Does this mean it's a positive or a negative 100? Good, negative 100. So Q is negative 100. However, we don't have work explicitly. We have to use a formula for that. Remember, our formula for work is negative P delta V. That negative sign is always there. So pressure is P, and that's an ATM. And volume is in liters. So work is negative P delta V. We're given the change in volume, and we're given the pressure. So work is negative 2 times 1 minus 4. So negative 2 times negative 3. So positive 6 joules. So that should make sense that it's positive because the gas is being compressed. So it's got a smaller volume, and you have to do work to that system. You have to do work to the gas in order to compress it. Because remember, gas wants to expand. So then we just have our delta E formula. Delta E equals Q plus W. Q is negative 100, W is 6. So we get negative 94 joules as our final answer. All right, and that's it. That is all I have for you. Yeah, sorry. Say that again? Yeah. So you multiply it by 101.3. So 6 times 101.3. So work is 607.8. Delta E is negative 100 plus 607.8. Good catch. Thank you. So you multiply by 101.3 because that's the conversion factor to get to joules. So I always see that with these problems. Yeah. Yeah. Oh, it's negative P delta V times 101.3. Yeah. All right, and if you guys want to stick around for a second, I have a survey, or evaluation, not a survey, that I would love for you guys to fill out, if possible. Well, you did do a survey, but this is for study union. This is for this 2 hours that I was talking at you.